Hello students, welcome back. Previously we went through the theory of Fermat's theorem. Here's the original form. And then here's the extension by Euler. Now let's do some application problems, such as these. Ready? How about this? A to the 103 power. Well, before this, let's make an observation. If you use this, a to the 12th power is 1 congruent to 1 modulo 13. Do you see that? So a to the 12th power is 1 modulo 13 because 13 is a prime number. Is that clear? And then 103. So a to the 103 power is a to the 96 plus 7. 96 is a multiple of 12. That is a to the 12th power to the it's the 8th power, isn't it? Okay, following the philosophy of this kind of problem, I'm doing this without calculator, so I'm a little bit slow here. And that's a to the 7th power, because this is 1. You see? By Fermat's theorem, a to the 12th power is 1. So this one here is 1. So a to the 103 power is down to a to the 7th power now. Okay, so far so good. And how do I reduce it further? Any idea? Well, one way to see that is to recognize that 8 is 2 to the 3rd power. So 2 to the 3rd power to the 7th power. We don't need equivalence here. And that is 2 to the 21st power. And how to do that? 12th power is 1, so I could do 2 to the 12th power times 2 to the how many? 21, 12, is it 9? Yeah, okay, all right, we got up to here, and 2 to the 9th power. We could get up to this, and then at some point you may have to do some dirty computation. 2 to the 9th power is 512, I think. Yeah, 2 to the 10th power is 1024. Or you could reduce it a little bit further beforehand. 2 to the 4th power. 2 to the 4th power is 16, which is 3 modulo 13. So if you use this, then this whole thing, 2 to the 9th power is going to be, let's see, 2 to the 4th power times 2 to the 4th power times 2, and that's equivalent to 3 times 3 times 2. Okay, this one I can do. 9 times 2 is 18. And that's congruent to 5 modulo 13. So it looks like I'm getting 5. Is this the only way? There must be other ways, but this is one of those ways that work. What did I do in my answer key here? Okay, that much is certain. 103 can be decomposed, and then 8 to the 7th power. And here in my answer key, negative 8 is negative 5. Because 8 is 13 minus 5, so negative 5. And negative 5 squared is 25. And 25 is negative 1 modulo 13, because 26 is divisible by 13. So reduce all those, and we got 5 like that. And that works too. Yeah, 8 is negative 5 and worked from there. Or you could do it this way. There can be many other ways. So you'll have to do some mod computations like this. And of course, if you want to check, you can always do this. Modulo 8 to the 103 power 13, and then Mathematica will do the computation. This kind of problems are no calculator problem. How about this one? 2 to the 11,213, and let's see, modulo 11. Again, 11 is a prime number, so we can use this. Anything to the 11 minus 1 power, 10th power is 1. This time the computation is actually easier, 10th power. So all I get is all I need to do is to get just 0. So this thing is 2 to the 11,2130 times 2 to the 3rd power minus 1. That's it, isn't it? This one here is divisible by 10. So this is 2 to the 11213 to the 10th power, or the other way around. And then let's do 10th power times 2 to the 3rd power, which is 8 minus 1, and that's, what is this? That's 1 modulo 11. So we have 8 minus 1, and that's 7 modulo 11. Okay, this one looked more intimidating with its number, but actually much easier than the previous problem. Or maybe I wasn't clever enough in the previous problem. What did I do there? Yeah, that's the same deal. 10th power. Mod 11, so we have 10th power, so the computation was easier. Next, this one is going to be Euler-Fermat. Not just Fermat, but Euler-Fermat, because 15 is a composite number. So, what is phi of 15? Phi of 15. Starting from 1, you have to count the number of positive integers between 0 and 15 that are relatively prime to 15. So 1, 2, and then 4, 7, 8, and 11, 13, and then 14. I'm getting 8. Okay, all right. So n to the 33 power minus n is n to the 32nd power times n minus n. Why did I take 32nd? Because I wanted to get a multiple of 8. 8th power to the 4 times n minus n, and that's congruent to, let's see, this is 1 to the 4th power. So that's 1. No, just 0 is fine. Here we need congruence because I just reduced this one down to 1. And let me put 1 here. Okay, this one here is 1. So we use this extended form here using the Euler-Torsion function for 15. We ended up with 0. I'm pretty sure I did it right. The number come out such not nicely, yes. Congruent to 0, modulo 15. And then the last problem, I don't have enough time. Also, we have an answer key here, so I'll leave you there. That one's left to the students, and we'll say section 2 is completed.